In this video lecture, we will go through some sample questions for computer organization. In this problem, every row represents the same number in three formats: decimal, binary, and hexadecimal. Notice that the binary format is actually 8-bit 2's complement format. Out of the three formats in each row, only one of the format for the given number is provided, and you have to figure out the other two representations. So for example, in the first row, minus 37 decimal number is presented. Now you have to figure out its binary and hexadecimal equivalent. Okay, likewise for rows B and C. So let's work on this. In part A, we are given minus 37 and we have to figure out its binary as well as hexadecimal representation. So because this is a negative number, the first thing we should do is we should come up with the representation for positive 37. So binary representation for positive 37 in 8 bits is 001000101. You can come up with this by using the division method that we have seen several times. And now to get the negative 37, just compute its 2's complement, right? So flip the bits, zeros becomes ones, ones becomes zeros, and this is your number. Now forget the original number and simply add a 1 to the flipped version, so you get 110110111, right? So this is your 37. So this is your minus 37 basically. Okay, so minus 37 in binary is 1101111. Now to get its hexadecimal representation, simply form groups of 4 starting from the right. So 1011 is B and 1101 is D. Okay, so in hexadecimal it is hexadecimal DB. All right. The second part B, was basically asking us to convert this binary string 000111110 into hexadecimal and decimal. So to convert this into decimal, recall that every position, every digit here represents a power of 2, right? So this is 2 to the power 0, 2 to the power 1, 2 square, this is 2 cube, and this is 2 to the power 4. We don't need to worry about these zeros because they do not contribute anything to the magnitude of the number. Now simply add the powers corresponding to the digits that have 1. So for example, 2 to the power 4 plus 2 cube plus 2 square plus 2 to the power 1, which is basically 16 plus 8 plus 4 plus 2, and this is basically going to add to 30. So this binary string is actually equal to decimal number 30. And finding the hexadecimal representation is straightforward. You simply again form the groups of 4 starting from right. So the original binary string was 0001 followed by 1110. So let's make groups of 4. So this is 1 and this is the second one. So 1110 is simply E, and this is 1, right? So the hexadecimal is hexadecimal 1E. Part C of this question is asking us to translate this hexadecimal string into binary and decimal. So let's first translate this into binary. A is basically 1010 and B is 1011. So this is the binary equivalent. Now so this is 1010 1011. Now to convert this into decimal, notice that this is a negative number, right? Because this the leftmost bit in the 2's complement representation is 1, so this is a negative number. So in order to get the magnitude of this number, we'll have to first compute its positive counterpart, right? So let's compute 2's complement of this number. So just flip the bits, ones becomes zeros, zeros becomes ones, and so forget about this original number and now add a 1 to this flipped version. So you get 10101010. Okay, so this is the positive counterpart. Now compute its magnitude. Again, this is 2 to the power 0, this is 2 to the power 1, 2 square, 2 cube, 2 to the power 4, 2 to the power 5, and this is 2 to the power 6. Let's simply add the powers of 2 that correspond to a value of 1 in this number. So we have 2 to the power 6 plus 2 to the power 4 plus 2 square plus 2 to the power 0. So this is basically 64 plus 16 plus 4 plus 1. So this is all going to add up to 84. 85. Okay, so the magnitude of this number is 85, and because the sign, the leftmost bit is 1, the number is actually minus 85. This is the answer. The answers are also summarized over here. So this is the answer for the first part, this is this for the second one, this for the third one. So the next problem over here is asking us to translate this IEEE floating point number into decimal number, right? So the first step here should be to translate this given number into binary. So this 4 in binary is basically 0100. So every hexadecimal digit becomes 4 bits binary. So again the next 4 is 0100. This 0 is basically 4 zeros, then next 4 is again 0100, followed by again 0100, and then there would be 12 zeros at the end. So this is our binary string. Now recall the floating point format. The leftmost number, this leftmost digit is your sign bit. The next 8 bits here, this is your exponent, and the last 23 bits, this is your fraction. Okay, so the sign bit is 0. This means the number is positive. Now recall that the exponent is always stored in excess 127 notation, right? So your number right now, your exponent is 1,000,000,000. We have to add minus 127 to this to get it back into 2's complement notation, right? So minus 127 is given by 1 followed by 6 zeros followed by a 1, right? This is minus 127. Let's add this to the exponent. So we get 1 here, 0 0 1 0 0 0. 1 plus 1 is 1 0, so we ignore this overflow carry. This is our exponent, right? So 1001 is basically 9. Okay, so our exponent is actually 9, and the fraction is given by here it is given by 0 0 0 0. There are 4 zeros followed by 1 0 0 1, and then there is a bunch of zeros at the end, right? Now recall that whenever we are storing the fraction in IEEE floating point format, we actually ignore this leading 1 point, right? This is always implied, so we have to add this to get the actual significance of the original number. So far we have the exponent is 9, the sign of the number is positive, and the significand is basically, the significand is given by 1.000010001. Okay, so let's write this number in scientific notation. So the number that we are looking for is actually 1.000010001 multiplied by 2 to the power 9. Okay, so after this multiplication, this floating point should move 9 positions to the right, which is basically here, right? So the number after multiplication becomes 100010001. Okay, so this is the number. Now let's translate this into decimal value. So again, powers of 2, this is 2 to the power 0, this is 1 2 3, this is 2 to the power 4 5 6 7 8, this is 2 to the power 9. Okay, so other zeros, these zeros are not going to contribute to the magnitude of the number, so we can ignore those powers of 2. So the number is basically 2 to the power 9 plus 2 to the power 4 plus 2 to the power 0, which is basically 512 plus 16 plus 1, which is simply 529. This is our answer. Alright, so this next question over here is asking us to convert the given floating point number 55.25 into IEEE representation. So the first thing we should do is we should translate this 55 into binary format, and then we should translate this 0.25 into binary format. So to translate 55 into binary format, you can simply use the division method, and you will see that 55 is actually 110,111. Now what about 0.25? Recall that every position after this binary point represents a power of 2, which is negative power of 2, right? So this is 2 to the power minus 1, this is 2 to the power minus 2, and so forth, right? So 0.25 is actually 1 upon 2 square, right? 1 upon 4, which is basically 2 to the power minus 2. So if we set a 1 here and zeros in all other positions, we get the binary equivalent for 0.25, right? So 0.25 is actually 0.01 in binary. Here it is. Okay, so given these two results, 55.25 is actually this number, 110.111.01. Now obviously this is right now not in the scientific notation, so let's represent this in scientific notation. So for to do that, we have to move this floating point to the left, 5 positions to the left. Okay, so this is the scientific representation. It is 1.101101 into 2 to the power 5. This is the scientific notation for the original binary number. Now from here we are very close. We just need to figure out the sign, the fraction, and the exponent field, right? So the exponent is 5. Now recall that the exponent 5 would be represented in excess 127 notation. So 5 in 2's complement is 8 bits, is basically 0 0 0 0 0 1 0 1. To translate this into excess 127, we have to add 127 to this, right? So 127 is basically 0 followed by 7 ones. So let's do this addition. 1 plus 1 is 1 0, 1 plus 1 is 1 0, 1 plus 1 plus 1 is 1 1. This is 1 0 1 0 1 0. So this is the excess 127 notation for 5. Okay, so which is also given here, 1 followed by 4 zeros followed by 1 0 0. Okay, now the number is positive, 55.25 positive, and therefore the sign bit would be 0. And what about the fraction bit? So recall, we assume that this 1 point, this is always implied, so we don't have to store this. So the fraction is basically 101101 followed by zeros, so that the total number of digits in this fraction field is 23 bits. Okay, so so this is our answer. This is the sign bit. These 8 bits are our exponent bits, and then these 23 bits is our fraction field. Okay, and we have simply translated this into hexadecimal. So let's quickly do that, right? So this is, let's make groups of 4 starting from the right. So let's erase this, right? So this is the first group, the second group, third group, fourth group. This is and then this is the next group. Okay, so this is 0 0 0 0, 1 1 0 1 is D, 0 1 0 1 is 5, 0 0 1 0 is simply 2. So this is going to be 2, and 1 0 0 is 4, right? So our answer is 425D 0 0 0 0. This is our hexadecimal representation. This problem over here is asking us to figure out the dual of this given algebraic expression. Now recall, the way to figure out the dual of any algebraic expression is to replace any ands with ors, any ors with ands, replace ones with zeros, and zeros with ones. Okay, so in this case basically you should replace this or with and, replace this and with or, and replace this or with and. So basically your expression would look like, the final expression would become x and not x or y is equal to x and y. Okay, so that is basically this option 5 over here. So that's the answer. All right, simplifying Boolean expressions. So let's start with the first problem here. Now notice that this term not of a or b is common in both these terms. So let's take this common out. So we get a or b not of this. Outside and inside the bracket we have c or d or e, and this is odd with 1, right? Now recall, 1 or anything is always 1, right? So basically this expression is same as not of a or b, and from De Morgan's law this can be written as not a and not b. Okay, so this is the answer for the first part. Let's work on the second expression here. So once again notice that this a and b is common everywhere. So let's take this out. So our expression becomes a and b, 1 or c or cd or cde or cdef. Okay, so once again 1 or anything else, this is always going to be 1, right? So basically this entire expression inside the bracket is reduces to 1, and your final answer is a and b. The answers are also provided over here for the same problems. Alright, so in this problem we are going to implement a 4 input odd parity function using an 8 by 1 multiplexer. So there are two parts to the problem. So the first is we need to create a truth table for this odd parity function, and then the second part is to implement this odd parity function using an 8 input multiplexer. Okay, so recall that an odd parity function will have an output 1 if and only if an odd number of inputs are 1, otherwise the output would be 0. So let's try to understand that over here. So here is the truth table. These are our 4 inputs A, B, C and D, and this is our output F. So in the first row here, notice that all the inputs are 0. So the number of ones in the input is 0. As 0 is an even number, the output of this row is 0. In the second row here, you will notice that only one of the inputs is 1. Okay, and 1 is an odd number. Therefore, the output of this row is 1. Similarly, in the third row here, you will see that only one of the inputs is 1 and all other inputs are 0 again. And because 1 is an odd number, the output is 1 here. Okay. In the fourth row, however, 2 of the inputs are 1 and 2 inputs are 0. Okay. So because 2 is an even number, the output of this row is 0. In the next row over here, again only one of the inputs is 1 and all other inputs are 0. Because 1 is an odd number, the output is 1 here. Okay. Similarly here, in the next row, again there are 2 ones in the input, and because 2 is an even number, the output of this row is 0. So likewise, we fill out this truth table for all the remaining rows, all the 16 rows. I hope this idea is clear. So that was the first part of the problem, to draw the truth table. Now the second part is asking us to implement this truth table using a multiplexer, right? Now notice that there are 16 rows in this truth table. Now if you were given a 16 by 1 multiplexer, implementing this multiplexer using a 16 by 1 implementing this truth table using a 16 by 1 multiplexer would be a very straightforward problem, right? So let's say this was your 16 by 1 mux, right? So you have only one output line, 4 control lines. So let's say you can feed A, B, C and D over here, and then you have these 16 lines over here. Okay, starting from 0, 1, 2 all the way to 15 over here. Okay, so in this case what we could have done is we simply copy each of these outputs one by one to these inputs, right? So the first output is 0, so we copy that 0 here, and the second row output is 1, so we copy that 1 here, right? Similarly, the third one goes here, the following 0 goes here, right? This one goes here, this 0 goes here, this 0 again goes here, right? The next two ones go here. Similarly, 0 0 goes here, then this one goes here, this 0 goes next, then these two ones go here, and finally this 0 goes in here, right? So if you had this 16 by 1 multiplexer, this was a very straightforward problem. However, the question says that you do not have a 16 by 1 multiplexer. You only have an 8 by 1 multiplexer, and you have to emulate this truth table, this 16 row truth table, using this 8 by 1 multiplexer. Okay, and that is why this is an interesting and challenging problem. So how do we do that? So let's first get rid of this multiplexer here. So we are instead given this 8 by 1 multiplexer. Okay, there are 8 inputs, exactly 1 output and 3 control lines. So now how do we emulate this 16 row truth table using this 8 by 1 multiplexer? So recall, by emulating a truth table in the multiplexer means that whenever a certain row, whenever you provide a certain row as input, so for example if you provide this all 0 0 0 0 for A, B, C and D, the output of this truth table is 0, so the output of the multiplexer should also be 0, right? Likewise, for any row, if you provide the corresponding inputs, whatever is the output of the truth table, that should be the output of the multiplexer, right? That is the goal. So how do we achieve that? Now the important trick here is to realize or observe some patterns in this truth table, right? So for example, let's divide this truth table into two parts, right? So let's divide this into two halves here. So in the upper half, from here, like the top half here, if you see, A is 0 for all of these 8 rows. Okay, only B, C and D have non-zero values. So if we had to, let's say, emulate on just the top half of this truth table using this 8x1 multiplexer, we don't need the value of A, right? We don't need, we can ignore A because A is always 0, and the output of an odd parity function is only impacted by the number of ones in the input. So A is not contributing to the output. So if we had to, let's say, emulate this top half, what we could do is, this would be a very straightforward problem. Let's say we feed in B, C and D over here in the inputs, and then we simply one by one hardwire these outputs of the 8 rows in order here in the multiplexer, right? So for example, this 0 can be copied here, right? The next one can be copied here, this one can goes here, right? This 0 goes in here, this one goes in here, this 0 goes in here, followed by 0 and followed by this one here, right? So now let's see whether our multiplexer is emulating the top half, right? So let's look at the, let's look at this last row over here, right? So this is 1 1 1, right? So if this B, C and D are 1, we will select this input 7 here, right? And this is 1, so 1 would appear in the output, right? And as you can see, that output of the truth table is also 1, right? Likewise, you can check for any other row. Let's check this one, right? So we have 1 0 1, this is 1 0 1. This selects row number 5 here, this 5 stores a 0, so the output should be 0, right? So 1 0 1, you can see here the output is 0, right? So the multiplexer is emulating the top half of this truth table, so this is fine. But now how do we account for this bottom half of this truth table, right? How do we do that? So once again we have to make an observation. So notice that just as in the top half the value of A is always 0, in the bottom half the value of A is always 1. And if you look at the values of B, C and D, they recur, right? So for example, here you see in the top row, in this row, the value of B, C and D is 0 0 0, right? In the first row here it was 0 0 0, next row it is 0 0 1, right? Here it was 0 0 1 in the top half, right? And so forth, all the way to 1 1 1 here and 1 1 1 here, right? So the values of B, C and D, they recur, they repeat themselves, but the value of A is always 1. So what that means is, in the bottom half, for every row, the output that is generated by BCD would be complemented from the output of the top half of the multiplexer. So notice that here, right? So let's focus on this row over here, right? So the output here is 1, the corresponding output was 0 in the top half, right? So for B, C and D 0 0 0, the top half had a value of 0, but now the bottom half for 0 0 0 has a value of 1, right? And similarly, the next row in the top, the second row had an output of 1. Now here the output is 0. So why is this happening? Well, very simple. Essentially, because now in the lower half the value of A is always 1, we are incrementing the number of ones in the input for all of these combinations of B, C and D by 1. So if originally the number of ones in the input of B, C and D combination was odd, in the lower half it would become even, right? Odd plus 1 is an even number. And similarly, if in the top half the number of ones in a row was even, in the lower half it would become odd, right? An even number plus 1 becomes odd. So that is why these outputs in the lower half, they are complement of their corresponding outputs in the top half. Okay, so now the question is, how do we capture that in our multiplexer? So there are multiple ways of doing this. One possible way is you simply add an XOR gate here, right? And feed A over here, the value of A over here. Recall that 1 XOR 1 is 0, right? And 0 XOR 1 is 1. So essentially what this means is A XOR 1 is always not A, complement of A. Okay, and similarly, if you XOR any number with 0, you simply get that number itself, right? So for instance, if you do 0 XOR 0, you get 0. 0 XOR 1, you simply get 1. Okay, so A XOR 0 is always A, but A XOR 1 is always not of A. So what that means is, here for the top row, the top 8 rows, when A is equal to 0, the values that we were getting originally would be intact. So a would be 0, so 0 XOR any value is that value itself, right? So we'll keep getting the same values as we were getting before. However, for the bottom 8 rows, when the value of a changes to 1, the output from the top 8 rows would be complemented. Okay, so let's see, let's check this for some of the rows, right? So let's check this for the last row here, right? So 1 1 1 1, right? So let's erase these values here. Let's say b was 1, c was 1, d was 1, and a was also 1. Okay, so if that happens, b c d is 1 1 1, so we select this bottom input, which is 1. So 1 XOR 1 would be 0. So the final answer we are getting is 0, and this is the output in the truth table is also 0, right? So now let's check the another row here, 0 1. So let's check this one, right? 0 1 1 1, right? This one. So b c and d are 1 1 1, but a is 0. Okay, so this again selects the 7th line here, which stores a 1. So we get 1 here. 1 XOR 0 is simply 1. So the final output would be 1. And notice that here the output is 1 in this truth table. Okay, so likewise you can check for other rows. So this is one way of emulating the 16 row truth table for odd parity function using an 8 by 1 multiplexer.